Hi everybody, my name is Doug Barr and it's a pleasure to welcome you to the St. Helena Forum for Innovation and Creativity. The Forum is an educational nonprofit with a mission to inform, entertain, and we hope inspire by presenting artistic performances and exchanges of creative and innovative thinking on a wide variety of humanities-based subjects. Today, we will be listening in on a conversation between our friend Dave Freed and Dr. Stefanie Milam about the recently deployed James Webb Space Telescope. Also known as JWST, the Webb is an infrared observatory currently 1 million miles from Earth, orbiting the sun and sending back the most astonishing images of our solar system and far, far beyond. Dr. Milam earned her BS from Kansas Wesleyan University and her PhD in chemistry at the University of Arizona. She then pursued a postdoctoral position at NASA's Ames Research Center to conduct laboratory studies of interstellar ice analogs with applications to astrobiology. Stefanie maintains a renowned observational program with radio telescopes and with space-based observatories to study comets as part of an international collaboration. Additionally, she conducts high-resolution spectroscopic studies of evolved stars, star-forming regions, and the galactic interstellar medium. She also has a laboratory dedicated to simulating interstellar, cometary, and planetary ices. In 2012, Stefanie was selected as the JWST Planetary Science Liaison. Under that role, she helped establish next-generation space telescopes as a planetary science resource, engaged the community in future observations, and assisted the project to ensure the capabilities of the observatory were suitable for solar system observations. In 2014, Milam was asked to continue her role through launch, which has, of course, already happened now, and she currently works with the project science team as an in-house planetary science expert. For those of you who are regular visitors to the St. Helena Forum, I'm sure you'll remember David Freed, a screenwriter, novelist, former investigative journalist for the Los Angeles Times, and a friend of the St. Helena Forum who interviewed evolutionary molecular biologist Dr. Beth Shapiro about biodiversity and de-extinction. Dave was an individual finalist for the Pulitzer Prize's Gold Medal for Public Service, the most prestigious award in American journalism, and he shared in a Pulitzer Prize for the newspaper's coverage of the 1992 Rodney King riots. Dave reported from Saudi Arabia, Kuwait, and Iraq during Operation Desert Storm, and he's a frequent contributor to national magazines, including, very germane for today, Air and Space, Smithsonian, and The Atlantic. He holds a Master's of Liberal Arts degree from Harvard University and currently teaches creative writing at the Harvard Extension School. Everybody, please welcome Dr. Stefanie Milam and David Freed. Hi, Stefanie. Hi, Dave. Thank you so much for being with us today at the forum.
Thank you, Doug.
Thanks so much for having me.
Hey, I know you guys have a lot to talk about, so if you're both ready, I'll turn the floor over to you.
Great. Stefanie, thank you for taking the time out of your very busy schedule. You'll find in the next 55 minutes or so, the vastness of my questions are surpassed only by the universe and my general lack of understanding of the universe. So I'm hoping that you will enlighten us. A bit of background. You are the only person of celestial note that I've ever met, with the exception of astronomer Clyde Tombaugh, who you may know was the discoverer of the planet Pluto in 1930, our ninth planet. So that was my big claim to fame up until our meeting, where I got to tell people I met the guy who discovered Pluto. Then Pluto got demoted. It was deemed, long after Mr. Tombaugh passed away, it was no longer deemed to be a planet, and it became, I don't know what it was. Now, as I understand it, it's a dwarf planet. So my question to you, with a bit of controversy, is why has Pluto been so misaligned, and isn't it time we brought it back to the varsity?
So Pluto is very different compared to the other planets in our solar system. And the best way to get a grasp of that is by looking at its orbit. So the orbit of Pluto actually passes and crosses the orbit of Neptune. It's a little off kilter from the plane of our solar system, and it's just weird. It doesn't look like any of our other planets as far as that particular orbit around the sun goes. It looks more comet-like, or what we know as Kuiper Belt objects, or trans-Neptunian objects, than anything else, except for it is one of the larger bodies in that population. So that's what obviously made it easy to detect. But it is a lot more like those objects than it is like our own planets in our solar system.
Like a comet.
More like a comet.
Which is your area of particular expertise. We're going to
Yes.
get to that in a bit.
Yes.
Yeah.
Now, as far as being a minor planet goes, that means that it's or a dwarf planet. It's bigger than these other bodies. It's bigger than a comet. It's bigger than an asteroid. And we have a number of dwarf planets in our solar system. And this isn't even the most planet-looking one that we have. Ceres actually looks and acts more planetary than Pluto does, with the one caveat that it hasn't actually cleaned out its orbit. So all of our planets, they basically consumed all of the asteroid material or cometary material in their orbit because they're so massive. And that material was actually used to make those planets. Ceres resides in the asteroid belt, so it hasn't actually cleared out all the asteroids and formed its own planet. And Pluto is the same. It resides in this trans-Neptunian region with a lot of other smaller bodies. And so, and then, of course, crossing the planet, the plane of the solar system, it makes it a little bit more eccentric in general. So we have other ones, though, that have rings. A lot of them have moons. These are really, really intriguing objects. So as far as if we want to promote Pluto back to its planet status, we'd have to bring all these other guys with us. And now, your mnemonic for remembering the planets, as we did as kids, becomes something like 15, 16 words as opposed to the 9.
Okay, so that's good to know. I guess then that I feel bad for all those kids over the millennia that had to put together planet solar system models, and they got the styrofoam ball that was Pluto. Okay, anyway, it's not every day that we get to chat with a NASA expert in rotational spectroscopy, observations, and laboratory modeling of astrochemistry and molecular astrophysics of the interstellar medium, evolved stars, star formation regions, and comets, with an emphasis on isotopic fractionation and astrobiology of primitive materials. Before you earned your doctorate in chemistry from the University of Arizona, go Wildcats, you got your undergraduate degree from a small liberal arts school in Kansas. And when we spoke earlier, you had indicated that you did an internship in winemaking, which I know is a subject that is near and dear to the heart of a lot of the members of our audience in Northern California. What did you want to be when you were growing up, and how did you get to be who you are today?
That's a very good question. And my story is a little scattered, I guess. When I was 6 years old, so I grew up in Houston, Texas. And when I was 6, I went on a school field trip to Johnson Space Center. So NASA's Johnson Center, where they train the astronauts and mission control. And I came home just completely elated. And I told my mom, when I grow up, I am going to work for NASA, or I'm going to be Madonna. So Madonna was already taken. So working for NASA became my new priority. I did dance. I was in ballet since I was 2 years old. I danced all the way. I actually had a dance scholarship to go to college. And at one point I thought professional dancing and ballet or a professional dance company was going to be something that I would do. But then I realized, dancers age and lose their jobs pretty quickly, and I wanted a little more security in my life. And so following the NASA trend was still the thing. The idea was I wanted to become an astronaut. And I thought having a skill set that an astronaut would need beyond sitting on a rocket or flying a jet plane, which, by the way, I was too short to do, meant that I needed to be a scientist. And I knew that NASA had this long-term goal of, either more experiments to do on the space station, returning to the moon to conduct more experiments, maybe building a laboratory there or a station where more science could be done, a potential future of going to Mars or other bodies in the solar system. And to do any kind of science, either on the space station or even on a body, would mean, having that skill set. And so I thought chemistry, which was something I was naturally pretty good at in school, was a great path. Learning how to conduct experiments, the scientific method, with an application that would be useful for something like an astronaut. So I pursued a degree in chemistry. I went to a small enough school that we didn't actually have a research program. And so I got a job at a local environmental laboratory. So, studying contaminants in groundwater and air pollutants and other things. And I realized very quickly that chemistry could be very, very boring, even though a very secure job, and decided that I didn't want to wash beakers for the rest of my life. And my advisor was fantastic and knew my passion for astronomy and working at NASA one day, and she introduced me to astrochemistry. So now my laboratory went from a building and a room washing beakers to the entire universe, where I get to study the chemistry of anything and everything with telescopes.
And so from there, how did you make the segue to actually working for NASA?
That's a challenging thing to do. And not everybody gets to have the path that I had. So my graduate degree was actually doing mostly observational work. So I was using telescopes to study chemistry in space. And that led to a lot of questions that needed to be solved in a laboratory environment. So there's things about comets that we just can't understand by just observing them. We need to actually do some laboratory simulations and understand the chemistry more in a controlled environment so that we can apply that to what we're observing. So there's a number of laboratories that make comets in a lab across the US and actually internationally. And a few of them are actually at NASA centers. One at NASA Ames Research Center in Northern California, which I was very interested in working with. And then another one that I was also interested working with is at NASA Goddard Space Flight Center, where I currently work. And so I asked if they were hiring and knew that it was a long shot because I hadn't worked in a laboratory my entire graduate degree. And they took a chance on me, and they thought that my observational work would be very good for them to have to apply some of the science they were doing in the lab. And I went to NASA Ames for my postdoctoral fellowship and learned how to conduct experiments and make comets in a lab. And I was then fortunate enough to be hired at NASA Goddard Space Flight Center a few years later, where I built my own laboratory now. And
wow, congratulations! Yeah. So you're as I indicated earlier, your particular area of interest is in comets. Why comets?
Comets are the cookie crumbs of our solar system. They're the leftover things of what formed our planets and tell us a lot about how planet formation starts, what material is actually recycled. So we know as stars are born and die, they go through this whole phase of, they're collecting material from space to make their own star and planetary system. There's a whole lot of processing that happens as planets are being formed. And then, of course, the star eventually dies through supernova or other extreme events. And when that happens, we want to understand how much of that material actually gets recycled. This is really important for the field of something like astrobiology, because we want to know what the molecular ingredients are of our solar system and other planetary systems, and see if we're making the same cookies out of every planetary system or if everything is coming from a different start. If we start with the same ingredients, that's really intriguing, because that means the potential for the same kind of chemistry that's here in our own solar system that formed the one instance of life that we know has the potential now for other planetary systems. And so we really want to know, our cookies the same as everybody else's.
God, that's what a great description of what sort of the overarching ambition of, I'm assuming, JWST is. Tell us, walk us through its capabilities and what have we. You could probably spend the next several weeks describing enthusiastically all of the things it has discovered thus far. But help us understand better what the telescope has taught us about ourselves thus far.
So I'm going to start with showing you this one slide. JWST was built and designed with 4 science themes. One was to detect the first stars and galaxies of the universe, so after the Big Bang. We wanted to see further back into the universe than Hubble has the capability to do. And to do that, we needed a large infrared space telescope, otherwise the James Webb Space Telescope. And that is what it was designed to do. But we also knew that it had, as a large infrared telescope, the capability of doing a lot more science than that. And we wanted it to be sort of an all-encompassing telescope the same way Hubble is. Hubble studies planets around other stars, our objects in our solar system, star formation, stellar evolution, galaxies, etc., supernova, whatever. And that is a full overarching sort of scientific observatory. And that's what we wanted the next great NASA observatory to be as well. So we came up with these 4 science themes where infrared astronomy really has a nice niche, and having this fantastic, powerful telescope that could detect first galaxies and stars of our universe meant that we could do extreme science in these other areas. So understanding how galaxies formed and assemble is something that the further we look back into our cosmic evolution, the more we can understand about how that process actually works. We can peer into giant clouds where stars and planets are formed. And that's something that you don't have access to at visible wavelengths like the Hubble Space Telescope. And so getting our night vision goggles to actually look and see these things happening and the dynamic processes that are occurring behind these big clouds is something that we were very excited about. And then even within the beginning of the James Webb Space Telescope project, planets around other stars started to be discovered. And we knew that infrared spectroscopy, so studying the composition of these planets around other stars, was something we just had to do with the James Webb Space Telescope. And sure enough, as the first planet was discovered around another star at the very early stages of the James Webb Space Telescope project, we now have over 5,000 that we know of. And we are studying as many of those as we possibly can now with this observatory to see what they're made of and if they are like any of the planets or satellites in our own solar system.
So you had indicated when we spoke initially that, and please correct me if I'm wrong, that really the ambition is not so much to try to seek out new life, not to be cliched, but really the ambition is is the pursuit of anomalies. Did I have that right? And
yes.
If I did, can you elaborate on that? What does it mean to be in pursuit of anomalies?
So when we're looking at these planets around other stars, we're not looking for life itself. And the best example I can try to explain or describe on why we're not doing that is because if you think about the images from Voyager looking back at Earth, or even from the Cassini mission when it took a snapshot of Earth, or even like the ones that we just saw from the Artemis mission looking back at Earth, it's very hard to see life. And so what we see is, especially from very distant perspectives, is we see something called the spectrum. So we're seeing what the atmosphere of the planet is made of. And then we put the pieces of what our atmosphere is made of together with how close our planet is to our star and what its orbit looks like and whether or not it's mostly gas, giant puffy atmosphere like Jupiter, or if it's something that doesn't have an atmosphere at all. So something like Mercury. And we put all these pieces together based on the knowledge that we have from our own solar system. And we try to understand what would make the composition of that planet be what it is, dependent on all these factors. So if we think about the history of Earth itself, our atmosphere has looked very, very different in its evolution from the very beginning to what we have today. And that includes having water. That includes having, during the heavy bombardment area, an entire atmosphere full of shrouded dust and hot gas. And at one point, we lost our entire atmosphere. Earth has gone through a whole series of evolutionary processes. And as we're peering at these planets around other stars, we're seeing them at very instantaneous moments of their entire evolution. So we have no idea when we're actually looking at it. So what we want to do is we want to look for things that look different. So if we're looking at a planet and we study the composition of its atmosphere, certain things are going to make that composition look awkward or different. And that is something that's a process that's occurring within that planetary system. Be it it's been bombarded with a comet or an asteroid, a moon sort of impact kind of event, or maybe it has geologic processes happening. Volcanoes, you can imagine all the soot from volcano changing the atmosphere, or maybe it just has dynamic weather. Think about dust storms on Mars or the Great Red Spot on Jupiter. These are the kinds of things that we're trying to look for and to see if there's something different about that planet. And if we find something that's different, that's giving us a short list of planets that now are in our pocket so we can study with more and more detail, especially as new telescopes are coming online. We have giant 30-meter telescopes now that we're building across the world. We have plans for the next big space telescope already. These are the kinds of things that we want to have a short list so that we can really hone in on them and focus and study them in more detail. So looking for the anomalies is really the key in trying to understand why they're anomalous and understand the process that's going on with that planet.
So if you're looking for anomalous processes and you're trying to find different rather than common, does that I'm not going to be able to articulate this question well to a scientist, but it strikes me that if the ambition, if the predicate is we're looking for anomalies, and maybe ideally we're going to find out whether we're alone or not alone in the universe, wouldn't you look more for things that we have in common, we as a species, and with our atmosphere and the geology of Earth? Wouldn't we be looking for things of that nature as opposed to things that where we can assume, given the gaseous nature of the planet or the chemistry of the planet, that there's no way in the world that it would form carbon-based life?
That's a great question, and the short answer is we have no idea if we are the only life there is. We have no idea that there's life that's like us.
Would you tell us would you tell us? You could tell us.
I'm an astronomer. I can't keep a secret. We tell you everything as soon as we possibly can. It's just how we are. We're more excited about our science than anybody else in the world. So we can't keep secrets. So what I'm getting at is, yes, I understand your rationale. We know one instance of life. We know that we need water. We know that we need liquid water. We know that we need oxygen and, carbon dioxide and methane are byproducts of our life processing here on Earth. We know that. But we have no idea if there's life somewhere else in our own solar system. And those environments are completely extreme. We're looking for life on subsurface oceans of moons around Jupiter. We're looking for life on Titan, which is a totally different type of chemistry. It's the only moon in our solar system that has a stable atmosphere, and it's totally different from ours. But we think that environment could potentially harbor something like life. So yes, we have a bias, and yes, there is a bias for us to start with what we know. So we are looking at planets that are in what we call the habitable zone or the Goldilocks zone. So it has to be a planet that's far enough away from its star that liquid water could actually stay and reside on a terrestrial body, but also not so far away that it's completely frozen or gone. And we're looking for terrestrial planets that have atmospheres, stable orbits so that it's not going extremely close to its sun or star and extremely far away, so the temperature variance is too extreme. These are all things that we are putting in our Goldilocks zones, and we are looking at these planets to try to understand what they look like. But it's, sort of the first step. We have many more steps to go, and looking and understanding what other planetary systems are like compared to our own is really the first step. And I have another fantastic image to show you about this. This is, or was, all of the known planets that we knew up to date, all the way to 2015, I think was when this one was last made. So we only knew about 1,700 planets at the time. And as I already mentioned, we know over 5,000 now. What you're seeing here is all the planets that we know and their orbits around their star. It's showing you how big those planets are or how small they are and how close or far away they orbit their star. And the most important part of this video is that the solar system, it's actually shown in these little gray dashed lines. This is our own planetary system. You can see our orbits of our planets are extreme compared to all of the known planets. Part of this is observational bias. It takes a long time for Neptune to go all the way around the sun. So if we're talking about transit spectroscopy, when we measure a planet passing in front of its star, we have to wait, hundreds or thousands of years sometimes for those planets to do a transit. Sometimes we get lucky, but most of the time not. There is some observational bias. But that being said, every single one of these orbits that you're seeing on here are smaller than most of the planets in our own solar system. So we're unique already. We already know that we're unique. And again, is this observational bias? Is this something that we don't have the technology or capability to study planets that are farther away from their stars? We're looking, we're doing the best we can. We have all sky surveys happening routinely. New ones are being built and getting ready to be put online, including the Rubin Observatory and the Roman Space Telescope will be launched in a few years. And they'll be looking at these planets, our planets around other stars, and trying to see if we can find any more. And we will find more and more and more, and seeing if any of them look or resemble anything like our own solar system.
So this imagery that we're looking at now is circa, if I have this correctly, it's circa 2012, and it's from Kepler, correct?
Yes. Yes.
The imagery that we see virtually daily from NASA, the stunning imagery that is released to the public and to among your colleagues who, astronomers who can't keep secrets, it's infrared imagery. How much of it is manipulated to create the imagery that we actually see?
Oh, that's a great question. So let's start with the Hubble Space Telescope. So Hubble actually operates at light in the visible part of the spectrum. So the same light that we see with our own eyes. But even the Hubble images that you see, for the most part, are what we call multicolor, 3-color type images. So what I'm showing you here is the image on the left is an actual Hubble Space Telescope image. And this is a multicolor image. So what they do is they take a picture in one color. So let's say blue. Then they take a picture in another color, let's say green. And then they take a picture in another color, probably red. And then they stack those images to build these beautiful montages of something that would look like what we would see with our own eyes. And this is as close of an approximation as we can possibly get without actually going to these objects and looking at them with our own eyes. And so we do the same thing with the James Webb Space Telescope images, which is what you're seeing here on the right. So again, this is multiple colors, but it's not colors that you would see with your own eyes. So we take a picture at one wavelength, and a picture at another wavelength, and a picture at another wavelength. And we just, for the quality of the image and for the understanding and comprehension of how these different wavelengths are change or trace different things within that image itself, we put them in colors. We try to match the same, process of, redder is longer wavelengths and bluer is shorter wavelengths, but it's all red light per se. It's infrared light. But that's what we're doing, is we're just taking pictures at different wavelengths of light to show us the different processes and different dynamics that are happening within these objects. So in the Hubble telescope image, you're seeing some stars that are mostly red and orangish, shining sort of in the background. If you look at those stars in JWST, they're bluer. That's because they're bright. In the visible light, they're redder, they're hotter, but they're not as hot as what JWST can actually see. And so the redder stuff is actually the warmer stuff. And so you see at the very tips of the pillars, these bright red sort of fingernails on the fingers. And that is actually brand new stars that are being formed. And they're starting to eat that gas and the dust around them. So that's how we actually make these beautiful infrared images and the spectacular colors that you see. It's not necessarily the colors we would see. It's just showing you different wavelengths of light sort of being reflected so that you can understand the different things that are happening in that image.
So beyond the red fingernails of new stars being formed, what are we seeing here? How many celestial bodies do these dense presences represent?
That's a fantastic question, and we have no answers. This is huge. This is the Eagle Nebula, or part of the Eagle Nebula. It's the Pillars of Creation, one of Hubble's most famous images, and actually one of my favorite Hubble images that's here on the left. And so what you're seeing is a giant cloud. So the same way clouds in our own sky block out light. So if you have a cloudy night, you can't see stars or the moon or planets in our solar system, or the sun during the day. We have clouds across the universe and across our galaxy. And these clouds are where new stars and planets actually are born. And so at visible light, which is what the Hubble Space Telescope image on the left is showing you, you're seeing that it's blocking out basically everything behind this giant cloud. You can barely see little red speckles throughout it, which are some of the brightest objects that are actually being formed, or even brighter objects that are behind the cloud. Now, if we put our X-ray vision goggles on, or our night vision goggles, and push us into the infrared image on the right from James Webb, you see that cloud starts becoming opaque. We can start seeing through all the gas and the dust that the cloud is made of, and we can see more glitter sprinkled throughout this image. A lot of it's background stars, background galaxies, but all the stuff within that cloud are the new stars that are being formed. And we can understand how they're being formed and the process that's forming them. We have so many questions about star and planet formation that we've never been able to answer because we can't study, or we couldn't study it with this level of detail. So knowing how many stars are formed in a region that's this big, this vast, knowing how big stars are formed versus small stars. Are most stars formed in multiplets, binary tertiary star systems, or they single stars like our own solar system? And then how their planets are then formed around them. Are they mostly gas giants like Jupiter planets, or ice giants like Neptune's? Or are they mostly these tiny rocky planets in the inner solar system? What does their asteroid belt look like? What does their Kuiper belt look like? These are all questions that we really are just starting to get our fingers on and understand. And the James Webb Space Telescope is just taking it to the next level and helping us really probe that whole process of stellar evolution.
You had indicated one of the things that I thought was particularly fascinating when we spoke earlier was that there's great competition internationally for telescope time, if that's an appropriate term. and that your particular area of interest is within our solar system, and that ultimately, I think you said something on the order of only 7% of, of available telescope time is allocated to exploration within our solar system. Do I have that? Did I have that correct?
With the James Webb Space
With the
Telescope.
James Webb, right? Could you walk us through how that process works? How do scientists from around the world vie to to get telescope time and to have their particular projects address the issues that they're interested in with the telescope?
That's a fantastic question. So the James Webb Space Telescope is an international partnership between NASA, the European Space Agency, and the Canadian Space Agency. And so a lot of people always ask me, does that mean NASA gets a third of the time, or the US gets a third of the time, Europe gets a third, and Canada gets a third? And no, that's absolutely not how time is allocated. What we do is we open up a call. So we solicit the entire world for scientific proposals to use the telescope. And so they have to write a justification for the science that they want to do, the modes of the telescope they want to use, the objects they want to study, and how James Webb the Space Telescope is actually going to help address those questions. Those all then go into peer review. So we have a panel of scientists. It's all organized by the Space Telescope Science Institute, who also runs the Hubble Space Telescope and does the same process for Hubble. And this group of reviewers looks at all of the proposals, and they rank them on scientific merit. Now, they are broken into sort of scientific categories. So as a planetary scientist, I'm not reviewing extragalactic proposals, for example. Only experts in that field are reviewing the proposals on extragalactic astrophysics. And then there's a panel of scientists that reviews exoplanets, and there's a panel of scientists that reviews solar system science. So what we do is we take all the proposals that have been submitted, and in cycle one, there was about 1,200 of these proposals submitted. And we rank them. Okay, this is the science we have to do. We have to study Europa and see whether or not the plumes of Europa look like the oceans of Earth. We have to study, this particular galactic field because we think that's where the most distant objects in the universe are going to be found, because it's kind of out of the plane of the solar system. It's out of the plane of the galaxy. It's a clearer view of, the universe. Or, star formation happening in the Eagle Nebula is something that we've never understood, so we have to observe this object. So once we have this ranked list, there's only so many hours in a given year, and we only allocate time for 1 year at a time. And we have to prioritize and sort of give a scientific balance of solar system science, exoplanet science, extragalactic science, star formation, supernova, whatever. And we have to come up with a list that includes all of our high priority projects now that fill that year's worth of time. So that means a lot of proposals aren't actually going to get completed. For the solar system, everything is really, really close. And most of the things in our solar system are really, really, really bright. So we don't need hours and hours and hours of JWST time to actually study Mars or Jupiter, for example. We only need moments of time. And in fact, we recently observed Mars, and we only needed 15 minutes to study Mars. Whereas people that are looking for, the far, far away galaxies, they need hours upon hours or days worth of time to sit and stare at that one piece of the sky to see if they can detect something further away than we've ever been able to detect. So the number of proposals in each category is not necessarily balanced by an hour per hour level. It's more on the number of programs and the scientific priority. So you said the solar system got 7% of time for the first year, which was fantastic. We did a great job. And we actually had a very high success rate for solar system science. But in general, across all of the proposals submitted, only about 250 were actually selected. So of those 1,200, it's like 1 in 4 success rate of proposals. And that's not doing the time balance either.
Was the 15 minutes to study Mars, was that approved, or is that on the table?
It was approved. It was part of a guaranteed time program. There are a number of people that were given time on the James Webb Space Telescope the first year and into the second year of science operations. Excuse me. Those are the instrument scientists, so the people that built our instruments. And then there's a whole series of what we call interdisciplinary scientists that were given time. So these were people that have been working with the James Webb Space Telescope project for the last 25 years. They were selected, I think, in 2002. I think it was back then. To basically help build the science priority and capability of the James Webb Space Telescope so that we knew that we were building something that was going to do the science that the community really wanted to do. And that's always a struggle with engineers and scientists. You know, we want more, we want bigger, we want better. And they're like, it doesn't fit in a spacecraft. So we're always challenged with these balances that we have to play. And so the people that were these interdisciplinary scientists were given a handful of time as well. And the Mars program for cycle 1 was part of the guaranteed time program.
So what did you hope to find in those 15 minutes? And what logistics are associated with positioning the telescope such that it is going to achieve your objectives?
So Mars is actually the brightest infrared object that the James Webb Space Telescope will ever observe, at least to date. It's so close to Earth. It's so hot. It is extremely bright for a telescope that's been designed to detect the first stars and galaxies of the universe. And we can only do certain wavelengths of light with the James Webb Space Telescope when we look at Mars. Because it's so bright, it saturates everything very, very quickly. And so a few of the science cases that we wanted to do was look for the Mars atmosphere composition and really try to hone in on whether or not methane is in the atmosphere that circulates or whether it's just localized sort of releases through the surface. We want to study other volatiles like water, carbon dioxide, carbon monoxide, see how that is affected by the weather and the general circulation pattern going around Mars. But again, all we had was a handful of minutes, and we were able to do all kinds of science and amazing results just with this blink of an eye with the James Webb Space Telescope. Comparable studies have been attempted from the ground, and it's taken months worth of time. You're competing for time on a ground-based telescope that's, already oversubscribed as well. But you need hours to actually get the full spectrum across the disk. Mars has to rotate so that you can get the full planet. Oh, and by the way, you're on the ground. So you can't observe during the day. If there's a cloud in the sky, you can't open the telescope. If it's raining, if it's snowing. So you have all these other challenges of observing from the ground that we don't have with a space-based observatory. And we have beautiful results. Our first data were actually already released. The first images, let me pull one of those up for you. So this is the first images that we released in a press release a month or so ago. So it's showing you maps across Mars that we did with the James Webb Space Telescope at 2 different wavelengths. So again, just 2 different colors. And what we can see is, craters, basins, a lot of surface features. But the more important thing was to actually get the spectrum where we're looking for the fingerprints of different molecules so that we can study the chemistry of Mars's atmosphere. And, we have detections of water, carbon dioxide, and the team is now currently working on the details of how much methane is there or other organics or maybe some of the more solid features, the silicate material, etc.
So how much interaction, if at all, do you have with the NASA teams that are managing the rovers on the planet?
I personally don't have a lot of interaction with them. I don't study Mars myself. When I became the deputy project scientist for planetary science on the James Webb Space Telescope, I wanted to ensure that all solar system science that we possibly could do with the James Webb Telescope could do it. And I don't study Mars. I don't study Jupiter. So I reached out to the astronomers that study Mars routinely, people that work with the Mars rovers, people that work on orbiters, as well as those that work in Jupiter and Saturn and every other object in the solar system that we could possibly point to, just to make sure that I was covering the full basis and know what suite of science do we actually want to do with an infrared space telescope that we can't do with a rover, an orbiter, a lander, or even with ground-based telescopes. And I worked with the entire planetary science community to understand what that meant. How fast does the telescope have to track a near-Earth asteroid if we really want to study one of them? What about comets? They also move really fast, and they're also extremely bright. What are the science topics that we really want to make sure that we cover with the James Webb Space Telescope? Pluto, how do you follow up something like New Horizons? And there's so much science that needs to be done and can be done with an infrared space telescope. And so I did work very closely with a lot of people that work on other NASA missions, just to understand where we are with the current state of knowledge, where we're planning to go as far as future planned planetary missions, and what JWST can do to fill in those gaps.
How much lead time do the people that are actually managing the maneuvering of the telescope, or the manipulation of the telescope, I should say, how much time do is devoted to the actual positioning the lens in such a way that it captures the images that you're in pursuit of?
That's a great question. So when all of the proposals are approved for a given year, we do a rack and stack. So we see when objects are going to be observable in the sky, and we're trying not to slew the telescope around a whole lot. We want it to move slowly and gradually across the sky. One, so we don't burn fuel or angular momentum. So we're optimizing the operations as best we can. But also every time you slew the telescope extreme amounts, the fuel does slosh around a little bit and we have to let it settle. So we try to move slowly and steadily across the sky as best we can. So a full year's schedule is penciled in, and we kind of move things around where we think, oh, well, this one might need a little bit more priority because for example, if it's a solar system object, we can see one side of the hemisphere at a given part of the year versus whenever we can observe it again. A couple of months later, you see a different part of that hemisphere. So sometimes we have to rejig things just a little bit. We iterate that schedule with the scientists that have submitted the proposals and understand whether or not they agree with what we have proposed of when they can observe. Then there's a short-term schedule that happens, and that's a couple of weeks out, where now the pencil becomes a pen, and we do our finalization of that schedule. So we're iterating with the scientists, as well as understanding, does JWST need to do a momentum unload? When was our last downlink? How much data are we going to be putting on board? How much data do we need for all the programs that are in the schedule or in the queue? And then we finally, 1 week before, we send up all of the observations for a week at a time. And that is when we have our final schedule, and that is what is in the queue. So there's a long term, sort of a short term, and then the final. And it's for one whole year we do this, and it's very iterative. Now, that being said, if something new discovery, supernova, interstellar object, new comet, a comet runs into the side of Jupiter, we do have a short-term access to the telescope. So we have what we call target of opportunity proposals, or short turnaround proposals, where we need to trigger the telescope to move to go observe the supernova that just went off. And we need to do it right now. And right now for JWST is about 48 hours. Because it takes time to do the uplink of the new schedule and fit things in and sort of rejig it.
And so how soon after the imagery is captured or downloaded do you have the opportunity to assess it?
So we have data uplink and downlink. I think we're on the schedule about twice a day, just depending on what's going on in the solar system, because we use the digital sky network. And whenever we have that access, I will say almost all the observations that I have been involved with to date, we've had our data in hand less than 24 hours from when the observations actually happened. So it's pretty quick.
So is that, I mean, do you have those kind of holy bleep moments where, you know, you get the data, you get the imagery, and it affirms what your hypothesis was, or is contrary to what your hypothesis was?
Absolutely. So I am going to start with one image, and then I'll get into some of the more fun stuff. So this is not a science image. This was data that we took of Jupiter during commissioning of the telescope. So once we launched from French Guiana on Christmas Day of 21, it took us a couple of weeks to actually get 1 million miles away from Earth to the second Lagrange point where we are in orbit. And then it took us about 6 months total to align the optics of the telescope, turn the instruments on, and make sure everything works. One of the things that we were told during commissioning was we are not allowed to science any images that come through for commissioning until after the first images are released for the James Webb Space Telescope, which was last summer. So this is commissioning data that we took of Jupiter. And what we were trying to do was understand, when we're looking at really, really bright things in the solar system, does all of the controls, pointing, tracking the telescope, to follow an object moving, how well does that work when we're looking at something extremely bright? So what we're doing is we took images of Jupiter and we moved it closer and closer to the guider. So a false science case for this would be if we were studying satellites of Jupiter and the planet itself got close to the guider. Could we actually do science on those satellites? And so these are less than 1 minute exposures. And the one on the right is showing you just sort of a stretched version of one of those exposures. So you can imagine turning up the lighting or darkness settings on your camera or your post-processing, whatever you're using. And we were just blown away. 1 minute, and we're seeing the rings of Jupiter in ways that we've never been able to see. We can see the aurora. We could see the Great Red Spot. We could see small satellites. Europa is so bright, it's saturating. It was mind-blowing. And of course, the project is all, don't science these images. And it's like, but look at it. Just look at it. It's so beautiful. So this was extremely exciting. And again, it was just quick snapshots to see what we could do. Once the science team that was actually slated to observe Jupiter got to get their hands on the telescope and do the things that real science would do, this is what we got out of it. And it's just absolutely stunning. There's nothing that has blown me away yet in the way that the first Jupiter images from the science team came in. The rings, again, the small satellites, the aurora, the storm structure that we can see, like the fine details of all of the storms going across the atmosphere, the clouds. This is absolutely fantastic. And then we went to Neptune, and it was like, oh my gosh, look at Neptune. Look how bright it is. Look how bright Triton is. This was mind-blowing. how well we could see the rings of Neptune and how bright they were. And it's not blue.
Well, what are you, that is remarkable imagery. What are you most excited about in the context of the JWST and what it's capable of doing?
Everything. Almost every single thing that we have looked at with this observatory so far has blown me away. I've been beyond excited about everything. From the planetary scientists, the Mars images, the Mars spectra, Jupiter, Titan now, even some of the small bodies. We're already getting just revolutionary science out of this observatory. We released this image of the L1527 protostar a few weeks ago, and it is by far one of my favorites. This is showing you star formation in a totally different level than what we saw in the Pillars of Creation. And this is an image of a star forming, which you can't actually see the star itself. It's just the evidence of the star forming. The star is actually in the very center of this hourglass. There's a little black line that almost goes right across the image of right across the center of the hourglass. And that's the disk of material. So you can think of the asteroid belt, the Kuiper belt, where the planets are forming around the star as it's becoming its own star itself. And it's pulling all of this gas and material in, forming its planets, forming its star. And there's so much energy going into it that it's actually blowing out all kinds of energy, which is actually colliding with all the gas and dust that it's pulling into itself. And so you see these fantastic little ripples going through the hourglass. That's where we're just constantly blowing out energy from this planetary system that's forming. We have not been able to image a disk like this with any other facility. This is the revolution that JWST has. We have capability to see things that we haven't been able to see at other wavelengths. We are now seeing star formation in a whole new light. We're seeing planet formation in a whole new light. We're seeing objects in our solar system with a resolution, capability, and wavelength coverage that we've never had access to before. This is going to basically rewrite the textbooks. We are in a whole new world of astrophysics and planetary science with the James Webb Space Telescope.
Well, that's terribly exciting. I mean, even from a lay perspective, it's very exciting. I noticed on your forearm, is that the solar system?
It is.
Okay. Is Pluto on there? I just wanted to.
I mean, so I have the Kuiper belt and the asteroid belt. So
okay. So
all the chromes are there.
We could spend weeks talking about this. This has just been utterly fascinating, and thank you so much. So I have just, I guess, one last question. You know, and not to be flip, but from a geocentric perspective, we have all grown up believing that we were sort of the center of everything, and that the solar system was referred to as the solar system. So with JWST and its predecessors, there has been a demonstration, obviously, that there may well be millions and millions of solar systems out there. So my question to you is, don't you think we need to name our solar system? And if so, what should the name be?
We are named. We are the solar system.
The solar system.
We have one sol, one sun. All the other systems are planetary systems. Oh. So there's your nomenclature.
I know, just an opportunity for maybe NASA to make some money. They could name the solar system like a football stadium or something of that nature.
Our sun is the sol, so we are the solar system.
Stefanie, thank you so much. This has been just fascinating, and I wish you much success as you continue to help us understand who we are and where we are in the vastness of the cosmos.
Absolutely. Thanks so much for having me.
Okay, my pleasure. Thank you.
And thank you all, wherever you may be in the world, for being with us today at the forum. To learn more about JWST, please go to webbtelescope.org. To find out more about Dave Freed, visit his website at david-freed.com. Over the past year, the St. Helena Forum has presented programs discussing topics as diverse as restoring the world's oceans, Martha Graham and the formative years of modern dance, hacking Darwin to reboot disappearing species, female pharaohs who ruled the world from ancient Egypt, and the role of television comedy in promoting second-wave feminism. Our audiences have joined the forum from all over the world for these presentations, and there are more already being planned for the new year. We'll keep you posted about the dates and the times on our website, shforum.org. And we'll look forward to seeing you again in a couple of months. Until then, please enjoy a safe, healthy, and happy holiday season. And finally, as we say goodbye, we'd like to thank the following people for their generosity in making the St. Helena Forum and its continuing programs possible.